Okay, welcome guys sa lecture natin for today, Principles of Steel Design. And for today's lecture, um, this will be actually divided into two parts. First part is about shear capacity of beams and deflection limits, which are the two concerns that we need to accomplish. Ano, yung other two limit states that we need to check for um, beams natin. And then later, we will have the second part, which is the design proper of beams. Pero ang focus natin, or we will just focus our attention sa design lang ng continuously braced beams. Ano? So, yung mas next topic noon, yung discretely braced, ibig sabihin yung LB is hindi siya equal sa zero. We will just tackle it when we go to the more advanced steel design subject. So for this lecture, ito lang yung or yung for this course, ito lang yung mako-cover natin. Alright? So let's start with shear capacity and deflection limits. So we will be discussing the shear strength of beams and deflection limits. So basically, these two are just a matter of substitution dun sa formula, understanding what the symbols or what does the code wants us to use depending on the result na gagawin natin dun sa mga formulas involved. Okay? So also, outcome natin, we will try to investigate yung beam section for shear and deflection. So yung local failure, this will be included na lang in your next still subject. Then to demonstrate how the formulas of the codes are applied, meaning when it comes to shear, strength, and deflection limits. So let us recall the limit state that we have discussed. Again, we are already through with the moment capacity of our section. Now we will try to focus ourselves with shear capacity and deflection limits. So as a reminder, for strength limit states, meaning we are ensuring the safety of the structure, we use as factored loads, and shear capacity is a strength limit state. And then when we deal with day-to-day performances, that is about service limit states, which is yung deflection, wherein service loads yung gagamitin natin dun sa pag-compare ng values natin with our capacity ng section natin. So let's start with shear strength. So basically again, substitution lang siya ng formulas and verification whether yung given section natin is falling under a certain category. Um, Fortunately for us, we are just focusing our attention to I-shaped lang or W-shaped sections. And W-shaped sections are usually very, very strong when it comes to shear. No? Yung shear capacity niya, when comparing it with or we are trying to get yung efficiency ng section natin, si shear capacity, medyo mababa siya. So, ibig sabihin, kayang-kaya siya ni beam, ano? Especially kung ginagamit siya for buildings or for vertical structures. Si shear strength capacity ni beam is maganda siya, no? Dahil na din dun sa ah, pagiging uniform ng section niya and also yung distribution ng thickness nung web tsaka nung flanges are hindi nagkakalayo. Okay, kaya maganda yung performance or very stocky yung beam natin. Okay? Pero when it comes to horizontal structures, let's say the beam is used as part of a bridge, ano? Um, wala nang usually mga I section W-shaped section na pwede para sa bridges kasi usually nire-require sa bridges is mas malalalim yung depth, no? So usually nagiging 1.5 meters, 2 meters o greater pa, no? And sa W shape or yung standard available sa hardwares, wala nang available W shape stable natin, ano? Usually ano lang ano? Ano ba yung largest possible natin? Let's check nga dito sa double shape natin. Sa double shape, depth na ah, largest is 44 lang ano? So, ayan. 44 inches lang. So, that is around 1.1 meters lang. So, kaya nangyayari pag bridges ang pinag-uusapan natin, built up yung section natin. So, um, kaya nagkakameron na siya ng ibang performance sa shear, kaya doon siya mas nagiging critical. Pero we need to understand how this formula works. And according to NSCP 2015, section 507, the design of member for shear or yung nominal shear strength natin na Vn is given by the formula 0.6 Fy Aw CV, wherein yung CV is yung web shear coefficient, AW is just the product of the overall depth. So AW is overall depth. So makukuha yun doon sa table times lang nung thickness ng web natin. Okay? Ayan na pala. Nakasulat na pala doon sa baba, no? Then yung KV natin is web plate buckling coefficient. So ang unang kailangan natin satisfy is to get yung ating gamma, no? 'Di ba yung H over TW, ito yung width to thickness ratio ng ating web. Okay? Ito yung width to thickness ratio ng ating web. Ah, kung maaalala nyo sa W shape section natin, then when looking at dito sa right side natin, we have two columns for compact section criteria. This is for the flanges and then this is for our web, wherein we discussed before that the first column pertains to the lambda F that we use in comparing yung to check for the compaction ng ating member and then ito yung ating gamma web. Okay? So for shear, yung sa web yung i-check natin. So ibig sabihin, kung given tayo ng section, kailangan natin kunin yung value ng gamma W. And then when we have the value for gamma W, we try to compare it with the following values or criteria. First and foremost, we need to compare it with 2.24 square root of E over Fy, wherein when using this formula, kapag English, again, E is 29,000 KSI, and then metric E is 200,000 megapascal. So, kailangan lang masatisfy niya yung anong to, condition na to na dapat less than or equal yung lambda W natin with this value. Kapag na-satisfy yon, ibig sabihin, ang gagamitin daw nating phi ay 1.0 or LRFD and then gamma or omega rather is equals to 1.5 kapag ASD tayo. Kasi again, we are still applying the LRFD principle, no? Na yung ating capacity wherein yung VN natin should be multiplied by a resistance factor, AFE, okay? And then our capacity should be greater than or equal to our um, applied loading or yung shear natin. Okay? So, yun yung main goal natin, di ba, sa LRFD condition natin. And that still holds true. But sometimes, hindi laging no, nag-greater than or equal yung lambda W dito sa factor na to. Kaya papansin ninyo, pag bumalik kayo dito sa W-shaped table, okay, meron kayong makikitang mga superscript dun sa mga sections natin. Let's say for example to, yung W44 by 230, meron siyang superscript na C at V. Okay? So, pag tinignan nyo sa baba, sa bottom, meron siya nakalagay dito V. Shape does not meet the HTW limit for shear. Okay? So, ibig sabihin nun, bumabagsak siya dun sa requirement na ito. Okay? And pag bumagsak siya sa requirement na yun, may iba yung value ng resistance factor mo and also your omega and possible yung value din ng CV kasi ito yung table for CV. Okay? So, kung halimbawa hindi nga masatisfy itong condition na to, no need to worry. Gagawin lang natin, pupunta ka doon sa next part, ano? Ito. And then kukunin mo naman yung value ng 1.1 square root of this one, ano? Pero meron siyang KV value dito. May multiplier siyang KV. Okay? Si KV saan makukuha? KV is taken dito sa table na to. Okay? And ayan naman, may mga condition din siya. For unsteepened webs or ibig sabihin yung H over TW natin is less than 260, we will use 5 down na as kV value. For stem or steady shape, 1.2 stiffened webs, okay, 5. Otherwise, ito. So, usually dito siya nagpo-fall under sa first condition. Okay? Yung HTW over 260 kasi when we check yung value ng atin dito sa lambda W natin, ayan ano, ayan, 38, 49. So, wala, usually mababa yung value niya, no? Na wala nag-greater than 260. Kaya usually, yun yung ginagamit na value ni KV. Okay? So, once na meron ka na ng KV, gagawin nun, i-multiply mo dito or gagamitin mo lang to and then, ayan, check mo ulit pa na-satisfy. Pag na-satisfy niya ngayon, yung resistance factor natin is 0.9 na. Okay? And then yung omega is 1.67 na. So, nagbago na siya, nabawasan na siya. Kaya, mapapansin ninyo, mag-iiba yung value ng capacity nung shear mo. And, again, this seldom happens sa W shape. Pero the uh, for the for formality or for knowing how to use the formula, we need to do it this way. Okay? Pero sabi nga natin, when we look at table 3-2, na we saw na may columns, no, for value ni shear. Okay? Pero again, you have to take note. This is for Fy is equals to 50 KSI. Once your Fy is different, you will not have a reference value para makita kung ano yung tamang number, ano? So, Uh, depende sa problem. If the problem insists na kailangan by formula yung method, you need to perform dun sa formula natin. And then, kung ano yung makuha mong value ng shear, i-compare mo na lang with the one presented on the table to verify whether your calculation is correct. So, mas madali mo ngayon check kung tama ba yung ginawa mo dun sa mismong procedure ng solution mo. Okay? And then, ayan. So, depende na kung saan siya papasok dito. And then, ayan yung mga gagamiting formula. So, kailangan lang sundan yan. And don't worry, you don't need to memorize again the formulas kasi this will always be provided to you when it comes to your examination. Okay? Same with the web plate backlink coefficient. Yung A daw is clear distance between the transverse stiffeners. So, clear distance between transverse stiffeners. So, ibig sabihin, kung ito yung ating I-shape section. So, yung bottom ng flange. Okay. Okay. So, kung ano yung value na to. Ayan yung A. Tapos, ayan, yung H natin, uh, given dun sa recorded video na sinend ko before, ito yung H na yan, ano, pag pina-calculate sa inyo. And then, this is the value of K, value ni K. Na yung mga values na yan, hindi kayo maliligaw dyan, ano, kasi nandito din yan sa diagram natin. Ayan, ayan yun. So, yun yung uh, may value ng H dito, no, sa table natin, may value ng K. Ayan, so, yan, pwede tayo mag-refer doon. Okay? So, again, we need to satisfy for LRFD. Ito yung formula natin and for AST. Okay? So, now let's apply to an example how to use the formula. A simply supported beam with a span length of 45 feet is laterally supported at its end and is subjected to the following service load. We have dead load of 35 pound per feet, live load of 95 pound per feet, and if Fy is 50 KSI and W14/90 is used, check the beam for shear. So, given tayo ng loadings, included na daw yung weight ng beam sa dead load. So, first, kailangan natin malaman is to calculate. Since shear pinag-uusapan natin, kailangan natin calculate yung ating ultimate shear. Okay? So, ultimate shear yung kailangan natin. And to do that, meron daw tayong simple supported beam. No? Walang diagram kasi. So, simple support. Okay? And then, meron lang tayong parehas given is uniformly distributed load kasi pound per feet yung unit, ano? So, ibig sabihin, meron tayo ditong, yan, nakaganyan sa kanya. Okay? Then, meron tayong makukuhang WU. Okay? Yung WU natin na yun is equals to 1.2 WD plus 1.6 WL. So, that will be 1.2 times 35 plus 1.6 times 95. Yung W natin. So, ultimate, ibig sabihin, ano kaya W? Ultimate uniformly distributed load. That will be 194 pound per foot. Okay? Ang kailangan natin ay shear. Okay? So, meron lang tayong simpleng condition, ano? Ito lang yun. Simple beam na may uniformly distributed load. Kailangan natin ng maximum shear. So, we can refer dun sa table 3-23 natin. Okay? And look at for simple beam na merong uniformly distributed load, ang maximum shear daw, nasan yun? Yung maximum shear natin is nasa support. Ang formula daw niya ay WL over 2. Okay? So, WL over 2. So, pwede natin gamitin yan. So, para makuha yun, VU is equals to WU L over 2. And then, we just substitute 194 pound per foot times yung length natin. Length is given as 45 feet. Okay, over 2. So, cancelled out yung feet. VU will be equals to 194 times 45 divide 2. That is 4365 pounds or 4.365 kips. Ayo, kilo pound. Parehas lang yan. Kips or kilopound. So, ito yung kailangan nating i-resist ngayon na value ng shear. Ano? So, yan yung ultimate shear ng section natin. Next is to use, calculate natin ngayon to calculate Vn. Okay? And Vn, as according to the formula, is 0.6 Fy Aw Cv. Pero we need to check first yung kanyang H over Tw. Okay? And our section is 14 by 90. So looking at our W-shaped table, 14 by 90 is somewhere, um, let's see kung nasaan, 14 by 90. Okay? Isa pa. Ayan. So 14 by 90. So this is 14 by 90. Okay? So ito yung, okay. So kailangan natin is yung HTW muna. So ito yun, ano, 25.9. So going back dito, we have 25.9. Okay? And ano daw ba yung 2.24 square root of 29,000. Ito yung E over Fy natin, 50. Okay? So, tingnan natin yung value niyan. 2.24 square root of 29,000 all over 50. We have 53.946. So, since ang kailangan natin satisfy, dapat siya ay less than. Okay, dito. No? Dapat siya ay less than or equal. So, since yung ating ano is indeed less than siya, okay? Therefore, ang phi v natin, kasi LRF ditong ginagawa natin, will be 1.0 and ang CV natin will be also 1.0 as shown din dun sa ating dito. Na-satisfy mo to, so ibig sabihin, ang PV mo, is 1.0, ang CV mo ay 1.0. Okay? So, yun yung ibig sabihin nun. So, now that you have that, ang kasunod natin is yung AW. We need the value of the depth and value ng ah, thickness ng web natin. Okay? Going to our W shape section. So, dito tayo. So, ang depth natin, and then 14. And thickness ng web is 0.440. So, 14 inches and 0.440 inch. So, area nun, that will be 14 times 0.44. That is 6.16 inches squared. Okay? So, ngayon, kompleto na yung formula natin. So, going to a new slide. So, Vn is equals to zero point 0.6 Fy AW CV. Calculate zero point 0.6 Fy is 50, AW is 6.16, CVA 1.0. So, Vn is equals to 56.16 times 1.0. That is 184.8 kips. Okay? So, kailangan natin ay phi Vn. So, that is given yung ating PV na satisfy natin kanina. 184.8 kips. So, therefore, ang phi Vn natin is 184.8 kips. Okay? So, ito yung value ng ating PVVN, yung ating capacity ng shear. So, let's double check kung yan yung lalabas dun sa 3-2. Okay? So, again, 14 by 90 tayo. Going sa 3-2, 14 by 90 is somewhere, so, to, dito. So, this is 90. Natira mo yung 14 dito, 145 yung kasama niya. So, masyadong mataas. 14 by 99, 14 by 90. Okay? And when we look at the capacity, makikita natin yung capacity. So, to. Then, do sa last column, PV, 185. Okay? So, 185 dapat. And ang nakuha natin to calculation ay 184.8, roughly 185. So, ayun siya, no? Yun yung dahilan kung bakit meron siyang value na 185 from table 3-2. Okay? Kaya nga again, yung usefulness nung AASC manual is actually giving us a shortcut or a readily available values para yun na yung gagamitin natin pag nagde-design. Pero kung may tatanong mo kung saan nakuha yung values na yun, ito yun. Ganito yung procedure niya. Kung bakit nakuha yung value niya. Okay? So, we still need to check it for beam, ano? Ang kailangan natin compare with the value of our ultimate, no? And makikita nyo, ultimate natin is 4.365. So, VU equals to 4.365 kips. Comparing it with VVN, that is 184.8 kips, no? So, sabihin, masyadong maliit siya, no? Pero, pasado siya. Therefore, okay, no? Kasi baka mamaya, pagdating sa moment or sa deflection, doon naman siya mataas yung efficiency, ano? Pero again, for most W-shaped section, masyado talagang sobra ang capacity ng shear. Okay? When we check the efficiency for shear, we have yung VU natin over VBN. So that is 4.365 kips all over 184.8 kips. Okay? Makikita nyo yung efficiency natin is 0.0236. Okay? So masyadong over design talaga siya. Okay? Or 2.36 degrees. Okay? So since okay siya, so siya ay adequate for shear. W14 by 90 is adequate for shear. Okay, so that will be our final answer or conclusion for this problem. Alright, so same conditions na yan do sa iba, no? If ever uh, your value for this checking will be greater than, gagawin mo lang, pupunta ka lang doon sa 1.10 and then you will use yung formula ng KV. KV is equals to 5 and then you will check again the values and then magbabago na yung PV mo, magiging 0.9 na. Pero yung CB mo will be the same. So, ganito lang yung checking niya for share. Okay? And then, once na na-calculate mo, you can always double check dun sa table sa column na to if your calculated value correspond dun sa actual value na ah inaano ni code. So parang ito, pang-checking mo na to, no? Pang-checking mo na agad kung tama yung ginawa mong calculation. Kapag may masyadong malayo yung discrepancy, um, it signifies na kailangan mong i-check yung calculation mo. Okay? So, yan yung para sa shear. So, ngayon for deflection. Yung sa deflection, same procedure that we have done already dun sa one example natin during laboratory last time. And ito, ano lang natin, reiterate lang natin, ano? So, in addition to being safe, a structure must be serviceable daw. When we say serviceable, dapat kaya niya mag-perform ng maayos nung structure natin, ano? Satisfactory daw na hindi nagbibigay ng kahit anong pangamba dun sa gumagamit o dun sa occupant, dun sa structure natin. Okay? So, yun nga, yung example ko from my other video, sabi ko, ayaw naman natin na habang naglalakad tayo sa isang floor, halimbawa sa suspended slab, ano, or sa isang floor ng building, ayaw natin na ah, gumigewang o lumulundo yung inaapakan natin o nagva-vibrate ng malakas, ano, kasi ang tendency tayo as human being, ang perception natin, malalaglag tayo pag ganun yung nararamdaman natin. And we tend to um, look for other ways kapag ganun yung experience natin dun sa area na yan. Kaya ito yung sa deflection limit. See, ang problema kasi kay steel, pag tinignan nyo yung AISC code and NSCP, wala talaga nakalagay kung ano yung um, maximum or yung limit na para sa isang condition. Kasi hindi siya katulad doon sa concrete na binibigay ni concrete kung ilan lang yung dapat na value. Ano? For steel, ang usually nagbibigay, it's either si client ang nagre-request na ito lang yung kailangang lundo ng building mo, pwedeng si architect, or depende sa experienced designer, no? Pero kung tayo sa case natin, we are just starting to learn how to design, um, meron suggestions sa International Building Code na mga values kung halimbawa floor beam yung purpose ng beam mo. Ang pwede mo daw gamitin kapag live load lang yung i-check mo for deflection is L over 360. And then kapag combination ng dead load and live load, we have L over 240. So, itong last part will not be applied to us kasi wala na tayong snow load. And kung wind load naman pag-usapan natin, si wind load is a transverse load. So, usually wala siyang component para kay floor beam, ano? Ngayon kay roof beam, meron dito sa last column kasi iba ang wind. Kung halimbawa nasa taas tayo, eh, then nandito yung ano mo, yung beam mo, yung load mo ng ano, ng wind na ko-convert siya into components, ano. So, halimbawa yung loading dito, no, naka-incline yung loading na ganyan kasi sa roof nga siya. Kukunin niyo yung component niya, i i i-co-convert siya into component. So, magkakameron ka ng value na galing sa wind, kaya meron siyang values dito. Pero for roof beam, depending on the type of condition, ito din yung mga gagamitin na value. Pero for our case, ang mga problems na ma-encounter natin, yung limit o yung deflection limit will always be given. So, para hindi niyo naproblemahan kung ano pa yung gagamitin. It will always be given sa problem. So your only task is to get yung maximum deflection for the given beam. And for uniformly distributed load, yung maximum vertical deflection daw natin is given by the formula. Okay? So if nag-iba yung condition ng ating beam, meron tayong pwedeng gamitin na table. Siyempre, 3-23. So you can use 3-23 and then look at the maximum deflection there. It's the same formula. Okay? Ayan o, maximum deflection, ito yung formula. So, depende kung anong masasatisfy na condition. Okay? So, if ever, halimbawa, combination siya ng uniformly distributed load tsaka ng point load, halimbawa concentrated like this one. So, kailangan, kung live load lang siya, pag-a-addin nyo yung deflection given by the live load na concentrated and then yung deflection given by uniformly distributed na loading. Okay? So, we can superimpose also deflection. Okay, kaya binigay ko din tong table 3-23 for us to utilize if ever nag-iba yung condition ng beam natin. Okay? So, um, so I guess we can perform one example for deflection also to demonstrate or to re-demonstrate yung ano natin, condition natin. So we have computed dead load and live load deflection for the 18-35 beam shown. If the maximum permissible live load deflection is L over 360, is the beam satisfactory? So, binigay lang na maximum deflection ay live load lang, ano? So, ang gagamitin mo dito, live load lang na loading. And again, kapag ang inaano natin, ang sinosolve natin ay deflection, ang ko-consider lang natin ay unfactored or yung service load lang niya. Okay, so let's perform this. So kailangan kunin muna natin yung maximum deflection due to our beam. No? Since this is a distributed load na simply supported, so 5/384 W L to the fourth over E I. Okay, so let us check 5/12. Oh, yes, correct, ano? So, yan yung formula natin. So, ang nawawala na lang dyan is yung data natin, ano, kung ano yung inertia natin. So, 18/35 tayo. Okay, so I guess inertia lang yung kailangan natin. Ix going to our W shape section. And then 18/35. Okay, 18/35. Ayan, yung naka-green na pala siya, no? Then Ix. So, Ix natin is this one, 510. Okay, 510 inches to the fourth. Okay, so substituting the values, we have 5/384. W is 50 pound per foot. L is 2.85 feet to the fourth all over. E is 29,000 kip per inches squared times inertia, that is 510 inch to the fourth. Okay? So, kailangan uniform yung section natin. So, kung deflection, ang advisable sa kanya is in inch dapat. Okay? So, itong nasa taas, pound per foot, gagawin natin kip, no? So, gagawin ko, multiply ako ng 1,000 pound equals to 1 kip para mag-cancel out to. Okay? Itong naka-fit to the fourth, kailangan ma-convert, kaya multiply natin ng for every 1 foot, there is 12 inches, and then release mo to the 4. Okay? So, matitirang unit ngayon are dito sa first one is kip per foot. Tapos meron tayong inch. Okay, naka-kip per foot na pala. Wait lang. Okay, so inch to the fourth. So, i-convert pa natin to yung isang foot na natira. So, 1 foot, 1 inch, 12 inch para mag-cancel to. Okay, so magka-cancel tong magiging 3 na lang to. Yung K sa taas, magka-cancel dito. Ito magka-cancel, magiging inch squared. So, magka-cancel to, may matitirang inch sa taas. Okay, so, pag kinalculate natin, 5 times 50 times 2.85 raised to 4 times 12 raised to 4 over 1,000. Ito pa lang yung numerator. So that is, idiretso ko na sa calc, no? So, over 384, 29,510. Answer is 0.0. Okay. 0.06022 inch. Okay. So let's double check yung unit. Pound per feet. Okay, I guess correct naman. So 50. Masyadong maliit lang siguro talaga yung loading, no? So let's include, hindi, kahit lagyan naman natin yung self-weight ng beam, hindi naman siya mako-compare dun sa live load deflection limit natin. Okay? 2.85 feet times 12 raised to 4 over 1,000, 29,510. Okay? So yun talaga yung lumalabas. Okay? So yan yung ating maximum deflection. So next is yung L over 360 limit. So that is L over 360. So that is 2.85 feet times 12 para maging inches, inch per foot all over 360. So yung limit is equals to 2.85 times 12 over 360. We have 0.095 inch. Okay? So since yung ating maximum is less than dun sa limit natin, therefore, adequate for deflection. Yung section natin. So, maybe super, ano, no, laki nung section na nagamit, kaya nagkakaganon. Okay? So, basta ganun lang yung pag-check sa kanya. Depende dun sa maximum deflection given by the beam, depende dun sa loading, and then compare mo lang dun sa limit natin. And then, that will be our value for deflection. Okay? So, that's it for shear and deflection limits. Okay? So, this ends the first part.